Okay, I'm gonna mute everyone. So Ryan and Ethan, you'll need to unmute yourselves.
All right.
Um, yeah, and if people later on, uh, if you can just stay muted unless you're asking a question, I would appreciate that. All right, welcome everyone. I'm so glad you could all join us. My name is Joanna Scharf. I'm the chair of the Cornish Energy Committee, and this is the educational forum entitled Fundamentals of Energy Smart, Cost-Conscious Building. And our speakers are Ethan Cole of Earthshare Construction and Ryan Hereth of Geobarns. I'm going to say more about our speakers in a moment. First, I need to say this. It's the policy of the Cornish Energy Committee that we do not endorse any particular contractor or product brand. This event is for educational purposes only. That being said, we have two excellent speakers tonight, and I'm thrilled to introduce both of them. Um, Ryan Hereth is the CEO of Geobarns, which is a Vermont-based company founded by Georgia Betty that has been building barn-style structures in the Upper Valley since 1992. Ryan started working as a carpenter for Geobarns in 2006, and then he became a partner and project manager for Geobarns in 2014. In the past 10 years, Ryan has helped build the creative structural foundations of Geobarns to adapt them into high-performance, durable buildings. Most recently, Ryan and his team have been focusing on studying comparative building assemblies, examining the impact and use of natural versus man-made materials to reduce embodied carbon, and balancing costs of materials and installation to provide healthy buildings for generations to come. Ethan Cole is the owner, CEO of Earthshare Construction, based in Lebanon, New Hampshire, which since 2011 has been producing high-performance buildings, remodels, energy retrofits, and weatherization projects in the greater Upper Valley. Ethan has over 20 years of experience in the trades and holds dual envelope professional and building analyst professional certifications from the Building Performance Institute, or BPI. He completed Net Zero Energy Homes training with the Northeast Sustainable Energy Association, where he is also a member of their Building Energy Bottom Lines Network. Ethan also runs the monthly BS and Beer events at Salt Hill Pub in Lebanon. That's BS for Building Science, which are gatherings of people interested in green building. And these events are where I've learned a tremendous amount about building science and where I got the ideas for these talks. So thank you very much, Ethan. Um, Ethan and Ryan will talk for about an hour. Um, and we might pause periodically during the presentation uh, for people who have questions about what was covered so far. So you can put questions in the chat. Um, but in general, at the end, when we get to, we hope to have like 30 minutes afterward for Q&A. When we get to that point, uh, we like to have people use the raise hand feature to ask questions. Um, and if you don't know what that is, using that instead of the chat box, and you find that raise hand button at the bottom of your screen under the image of a heart and labeled react. So under the reactions or react, you'll find a little raise hand thing. Um, I hope you will all find the information presented here as fascinating as I do, and I want to thank both Ryan and Ethan for being here. We are tremendously grateful that you are giving us your time today and for sharing your expertise with us. All right, so I'm going to turn it over to them. They will be talking. I don't know. We'll see how how they're going to organize this.
All right. Yeah. Ethan, do you want to kick it off here?
Yeah, absolutely. Do you want to just put it back to two slides real quickly? I guess first off, I just wanted to say thank you everybody for being here. Um, and encourage you all to put out questions at any point. We want to make sure we address the questions that come up. We're going to be covering a really broad range of topics in our effort to introduce everybody to some of the fundamentals, which it turns out are not as simple as we might hope. Some of them are, and some of them are not. So please feel free to put your questions out at any point into the chat, and so we can make sure to address them. And Joanna gave us a great introduction. Thank you, Joanna, for that. And just to touch upon, just to give you guys a little bit of context, Earthshare Construction we do new construction, we do renovations. Yeah, you want to show us the next slide, Ryan? We are a triple bottom line company, which means we're committed to people, planet, and profit. I just want to put in a plug for Nessie. They run a really great peer mentoring group for businesses that are values driven, committed to the triple bottom line, and so they can share expertise and all kinds of resources. It's a great organization. So we also do weatherization. We do new construction, renovations, and weatherization broadly with a focus on energy efficiency.
All right. Sorry.
It's okay.
Yeah, I appreciate you plugging that info and providing that info for us, Ethan. Everybody, really appreciate you being here tonight. My name's Ryan Hereth. Julian did a great job of giving a little bit of background about me and our company, the services that we provide primarily in New England, as well as the Mid-Atlantic, our land planning, design and pre-construction services, and construction management, as well as the actual carpentry and construction of the buildings. One of the things that kind of sets our company apart is I think we're a service-based company who values building relationships as much as we do the buildings themselves. And we're continually trying to improve our processes, and a lot of what I've learned in the last 10 years is working with people like Ethan, and having the opportunity to really open up the dialogue. I think I'm really grateful to have this opportunity, because as Joanne also mentioned, we have some great resources in the area like BS and Beer, and they're if as much as you guys can take part in these conversations, it's really important, I think, to kind of just open things up so that we can all learn. I'm excited. I'm sure there's things that I'll be learning tonight with some feedback and some questions from you all as well.
Yes, likewise. And just a little note about our industry. We're telling you about ourselves just to give you a little bit of context. The construction and design industry is really broad and diverse, and the areas of knowledge we are either expected or have the opportunity to become expert in are really broad. And there's a lot of great companies and people doing this work, and there's a lot to it. So I just wanted to point that out, and maybe I'll touch on that later. We want to give a thank you to some of our colleagues who have generously let us use slides from their presentation tonight. Steve Spatz from Efficiency Vermont, Gwen St. Sever from Bite the Frost Net Zero Designs, Jacob Deverecusen from New Frameworks and Builders for Climate Action, and 475 High Performance Building Supply based in New York. So the fundamentals of energy smart, cost conscious building. We're going to cover a lot of ground here, and some of the questions we're going to dive into are: what makes the most durable, energy efficient building envelope? How to safely and economically achieve building tightness, the best wall and roof assemblies money can buy, vapor barrier versus air barrier, some of the differences and the importance of those, how best to seal around windows and other framing transitions, and continuous insulation, pros and cons of some different types of insulation. Some of these topics we're going to go into more deeply than others, and we'll be leaving time for questions at the end. And as you can guess, the answers aren't always as simple as we'd like, but these are starting points. The fundamentals of energy smart building, we got a little animation here. Let's define a little bit about what energy smart means. For starters, it refers to a building that uses less energy. And we can refer to that, one way we can refer to it as operational energy, the energy that's used to heating and cooling of the building, lights and outlets, which is sometimes referred to as energy use intensity or EUI. And also durability. An energy smart building is one that's going to be durable. It's going to last a long time with minimal ongoing maintenance. Some of the other topics that are relevant to Energy Smart that we're not going to spend as much time on are resilience, a building that can sustain a grid disruption or natural disasters without being lost, reduces impact on the surrounding site and the ecosystem, consumes less embodied carbon to construct. We'll touch upon that, but there's been some exciting advancements in recent years allowing builders to understand the embodied carbon emissions of building materials. Energy consumption can be, when it's renewable for a building, that can have substantial impacts. And so choosing electricity over fossil fuels, choosing renewable power options, whether it's site supplied, community solar, or the recently formed Community Power Coalition of New Hampshire. And also thinking about transportation energy and what's going to be required to get to and from the building.
So construction methods and techniques, our relationship to buildings, access to grid-tied power and energy has evolved dramatically in the past few hundred years. In the 19th century, we were building drafty structures with regionally accessible natural materials and inefficiently heating the buildings with fossil fuels. Designs often incorporated centralized fireplaces to heat the core of the home, or in some cases, fireplaces dedicated for each of the rooms independently. In the 20th century, we started implementing man-made materials into our buildings, improved our insulation, in some cases, introduced mass production of materials with promise of greater energy efficiency, material durability, and longevity. We also gained broader access to grid-tied power. In the past 30 to 40 years, we've come to learn that our buildings are complex systems that we need to look at as a holistic design. The industry is entering into a new phase of understanding about energy efficient design, material selection that enhances performance, durability, and environmental stewardship.
This slide introduces us a little further to the concept of energy use intensity, which is a measure of a building's energy efficiency calculated by dividing its total annual energy consumption by its total floor area. It's typically expressed as thousands of BTUs per square foot per year. And I know this is a little technical, but one of the points I want to make is that it's something that one of the audience members was touching on earlier. This is complicated stuff, and the amount of energy we use is not very visible to us, and we don't really have a common vocabulary for it. So energy use intensity is just one metric we can use to better understand how much energy we use. So here, this table shows us that oil contains 138,000 BTUs per gallon, and electricity, by comparison, has 3,412 BTUs per kilowatt hour. So these are three different homes in Lebanon, New Hampshire. The bottom two have undergone weatherization and actually more extensive weatherization, which I would call a shallow energy retrofit. And the top one was a candidate for the New Hampshire Saves weatherization program, and it qualified. So you can see we've got the square footage of the homes, and I've indicated that one of them was multifamily, one was a single family, and one had 2 units. I also put in the number of occupants for the sake of conversation and consideration. The fuel use here, oil for 2 of them and electricity for the third one, and the number of units of fuel they consumed annually. So you calculate those and convert the electricity to BTUs. You can see the total energy consumption. And then the next column is the energy use intensity, the number of BTUs consumed per foot per year by those buildings. The two at the bottom that have undergone extensive weatherization, those are impressive and satisfactory numbers for existing housing stock that has had an overhaul, has had work done. The top one qualified for New Hampshire Save's weatherization program because it's over the approximately 60,000 BTUs per foot per year required to qualify for that program. Then we just show a conversion into kilowatt hours per foot per year, and then for the thought exercise, how many BTUs per foot per year are being used per person. So this concept of not really knowing how much energy we're using, whether it's for transportation or our house and all the other things we use and consume, is something called energy blindness. Thank you. I think that's enough on this slide.
Yeah. So EUI is one metric for how we measure the performance or energy use of a building. In understanding and properly constructing our building envelope assemblies, the control layers within those assemblies are the methods for how we achieve energy efficiency and durability. The fundamentals of energy smart design or building design. So some of the characteristics and principles here that we'd like to cover with you are specifically the geometry of a building. So the more simple the geometry of the building, the less energy it's going to require. And conversely, the more complex the geometry, the greater cost to build and operate as well. The smaller the buildings tend to use less energy. Specifically, multifamily buildings use less energy per capita, per unit, per person, per building. Similarly, site design and building orientation are also key factors. Fenestrations, windows, and doors have a big impact on building performance due to their relative reduced thermal efficiency compared to walls and roof assemblies surrounding them. Building envelope. We want to talk about our building assemblies, the walls, roofs, and foundations, and specifically making sure that we have an envelope that's airtight and durable. We'll touch on some of the operational energy use, the heating and cooling energy use intensity that Ethan was just talking about, the EUI, the mechanical systems within the building, appliances, ventilation, both for the equipment in the building as well as occupants. Lighting and plug loads are also factors that we're probably not going to be able to get into today, except for maybe in the chat afterwards.
So this is just a nice graphic from 475 that shows the components of a high performance building. We need to pay careful attention to continuous insulation at the entire perimeter of the envelope, especially including cold spots. There's always going to be some vulnerable spots in an assembly at transitions and other such locations. You want to have great windows. If you're going to have a great envelope, you want to have great windows to go along with it. When you're going to make a building tight, you need to bring in mechanical ventilation, and air tightness is the primary driver of energy efficiency. So Joanna posed the question about how to safely and economically achieve building tightness. And I think this comes from a couple of places. One place is we've all heard the notion that a building needs to breathe. And it's well known in modern construction that is not true. The occupants need to breathe, and a building needs to be able to dry out. So the notion that a building needs to breathe, and also the recognition that if you do not manage the moisture in your building adequately, you can have trouble. So in order to safely achieve building airtightness, you need to make sure your assembly is vapor permeable, that it can dry out if it gets wet. You also need mechanical ventilation. The occupants need fresh air. And if there is a combustion appliance of any kind, make sure it has clear, closed combustion air and exhaust paths. We advocate for no fossil fuels, but if you're going to have fossil fuels or a wood stoves are okay. They just need closed combustion, dedicated combustion air, and a flue. Ryan, you want to talk about economics a little bit?
Yeah, we need to make sure the air barrier is clearly identified and detailed during the design phase. It's critical for coordination with our crews on site, as well as ensuring that we have continuous air barrier on both sides of our assembly, which we'll get into later. We also we're constantly designing the process and sequence of that building with that air barrier in mind as well. And we'll get to that as well later as well.
This is
So
our one
now,
slide that shows a ventilation system. Yeah, just emphasizing the importance of ventilation. And I'm sure we'll have some, Joanna will probably have whole talks on ventilation in the coming months.
yeah. Generally, just want to talk a little bit about insulation types. We're not going to spend a whole lot of time on this today, but the widely used ones in the industry are fiberglass, foam plastics like polyiso, EPS, extruded polystyrene, cellulose, which is a shredded paper, rock wool, mineral wool, which you may be familiar with, wood fiber insulation like from Timber HP in Maine, Gutex or Styco, which are coming from overseas, and straw panels and straw bales.
So the best wall and roof assemblies money can buy. This is a question that we love to debate, but also needs to be defined. So how do you measure it? Do you measure it by thermal performance and its resistance to heat loss? Do you measure it through affordability, through the carbon emissions of the building, either during construction, during operation, or both, or the longevity or durability? Some of the best wall and roof assemblies money can buy, include, and we'll talk a little more about these, but a double stud wall or otherwise thermally broken stud wall with cavity insulation only in the cavity. Or you have exterior continuous insulation where it's put on the outside of the structural building cavity. Then these days, as you probably all know, there's all kinds of companies that are offering panelized walls and modular units to build your homes, and they're all there's a lot of good products out there, and they all can achieve similar results. People often ask, what's the best way to do it? What do you think of this? What do you think of that? And there are pros and cons to each. They're not as different as you might think, and you really have to define what your goals are and what your values are in order to make those kinds of decisions. So this just illustrates the double stud wall, which can be done a number of ways. But as you can see here, you have an outer structural wall generally. And on the top left here, you can see it's a 2x4 structural stud wall. And on the inside, you have a 2x3 framed wall. And the entire cavity is filled with, in this case, looks like it's probably cellulose. That's what we use. And so the space in between the stud walls is the thermal break, so that the wall is not a continuous thermal bridge. You could build the entire wall out of a 12-inch, a 2x12, a 12-inch stud, but then you'd have bridges at every framing member. And that's what this gets away from. It also uses less wood. Yeah, the bottom wall is similar. It just uses a 2x6 and a 2x4 wall for the interior, but they perform very similarly. This slide illustrates exterior continuous insulation. It's a slide that's dedicated to from Steve showing the control layers in an assembly. So I'll highlight those as well, but you can see the bottom shows, going from the bottom, you've got a layer of sheetrock. And then behind the sheetrock, you have a vapor retarder. And we'll talk more about those. Then you have your 2x6 wall, and the yellow indicates the cavity insulation there. And then the next white line is the plywood sheathing, structural sheathing. Outside of that, or right on top of the plywood sheathing, is in this case, and quite often, the air barrier, which can be achieved a number of ways by taping the plywood seams or using a membrane. Which is, in this case, it appears that the air barrier is also the water resistive barrier. So if water gets behind that outer exterior insulation, the design here is that the water will be able to run down there. So then you have a layer of exterior continuous insulation, and the best product to use from an environmental standpoint these days is wood fiberboard, which there is a plant in Maine that is offering and will continue to be offering more. It's not easy to get the stuff right now. And Ryan just mentioned them. They're called Timber HP. You can also more commonly and historically, the exterior continuous insulation has been achieved with foam plastics and also mineral wool. So then you have a gap. The white space there is the rain screen. So if water gets behind the siding, it can drain down there freely, and the siding is also able to dry in both directions. So that's a critical piece of an assembly that will have greater longevity. Then you have the siding, and the water shedding surface is indicated in purple. So that's where you want the water to stay, but you're also planning for the inevitability that some will get behind the siding.
Okay, so we've talked a little bit about our wall assemblies there, the envelope of the building. Now we're going to take a second to talk about thermodynamics. So conduction, convection, and radiation.
Excuse me, Ryan, I apologize. I wonder if this might be a good, before you go into the thermodynamics,
Sure.
to see if anyone has questions about what you just talked about, the wall assembly and the different layers. People could put something in the chat or just unmute and speak up. There were a couple of questions in the chat, but I don't know that they apply.
And just so you guys know, we will be diving deeper into the wall assemblies.
Oh, you will? Okay.
Yep. We'll be
Okay.
kind of coming back to them.
Sorry.
Yep, it's okay. So thermodynamics comes into play because conduction, convection, and radiation are three primary types of heat transfer occurring in our buildings. And they're constantly interacting with our walls, roofs, and foundations, which absorb, release, and release heat through conduction. Convective air leaks out at the building seams between the walls, roof, and foundation, and penetrations for exterior plumbing, light fixtures, etc., if not sealed well. Radiation from the sun can come and can actually overheat our buildings if they're heavily glazed. So here we have a comparison of building types, or building 3,000 square foot buildings from one of our colleagues here, Gwendolyn Saint Savar, and she was looking at three different buildings, again, all 3,000 square foot homes. And we're going to observe how the surface area of these buildings varies based on their relative geometry. So the greater the surface area equals a greater heat loss or gain potential, which means there's going to be more energy required to heat or cool these buildings. In scenario A, or style A, it's a more complex geometry with multiple volumes intersecting. It's a two-story building with a 2,000 square foot footprint, 2,800 square feet of exterior wall surface, and 3,200 square feet of roof surface, a total of 1,080 linear feet of seams. This is just a visual of what those wall surfaces, roof surfaces, and foundation surfaces look like for style A. Style B is a more simple two-story cape home with a 1,750 square foot footprint and a 1,600 square foot wall surface. It has 2,500 square foot of roof surface. Relative to style A, this is a very efficient use of floor space with a considerable reduction in surface area and seams. Again, a visual of style B's surface areas. Style C is very simple geometry, similar to style B, yet with an even smaller footprint of 1,150 square feet and a taller eave wall. So less square foot per floor, but there's 3 floors inside, which, again, add up to that 3,000 square feet. The key difference between C and B here is that the square foot of the walls has increased from style B, but the surface area of the footprint and the roof have also both significantly decreased. if we look at the total square footage of exposed surface area to the exterior envelope, we can see how the geometry of the building plays a big factor in how there's opportunity for heat transfer, heat loss, and gain in our buildings with buildings that all have the same square footage. So when we're designing buildings for energy efficiency, we need to be thinking about simple geometry. So this next slide is really to depict another example of this. We have two buildings that are about the same square footage, just right around 1450 square feet. The only differences between these two buildings beyond that like very slight square footage difference is that the exterior wall surface area, the windows and doors locations, and the quantity of those windows and doors. The impact between these buildings because of that building geometry and surface area is a 60% increase in the heating and cooling demand. You can see the building on the left here has a 12,000 BTU square foot heating load, and the building on the right has a 20,000 BTU square foot heating load.
That's the energy use intensity number I referred to earlier. And when building new and designing for high performance, you can get that number nice and low. This slide indicates the impact of air tightness as the number one driver of energy efficiency. Over on the left here, we have a code built house, which is in some states 5.0 air changes per hour at 50 pascals. We'll talk about that more later. And then you have the International Energy Conservation Code, where if you achieve 3 air changes per hour, you save 35% energy. Less than 2 air changes per hour, 50%, and the passive house standard of 0.6 air changes per hour at 50 pascals allows you to save 61% of your energy.
Yep. So the big takeaway here, folks, is that the two biggest levers we have to pull on to be able to create energy efficiency in our buildings is simple geometry and getting our buildings airtight.
I just want to speak to so someone in the chat is asking a question about ventilation. They've got having a house being built, and we can talk more about that ventilation later. I think we'll have time for that, because that's critical. But I would say if you're building a house, you want to know what your air tightness target is, what your builder is aiming for, and how that's going to impact the performance of the building. Here we go. Just outlining the importance of the control layers. It's really important that we flash our house, design our buildings to shed water, and so that it does not rot away. Secondly, we want to control for air loss as the number one driver of energy and indoor air quality. Third, we want to control vapor movement and prevent it from getting into the cavity. And when it does, we want it to be able to dry. And lastly, the thermal envelope, the insulation, we want to have the right amount.
So building envelope water control. Successful building detailing and construction relies on redundant systems. In this case, we want to shed it. So our primary and secondary layers of protection in the photos here are roofing, gutters, and siding. The protection starts with the roof, which sheds water down around the building, and in this case, into those gutters, into a perforated pipe that feeds a vegetated swale/rain garden. Wind-driven rain hits wood siding, which is strapped out on a rain screen or a lime plaster, as you can see on the white surfaces here, which provides protection to the surfaces within that wall assembly below. Here we have two examples of what's under the hood, our rain screen. So the next line of defense in our wall assembly from that exterior cladding, we then step into our rain screen. This rain screen provides a drainage plane for any moisture that does find its way past that cladding or underneath the roofing behind our siding, which also promotes a vapor drive. So when the sun hits that siding, it's going to, with that air gap behind it, the siding will heating up the air behind it through conduction, and then create a natural vapor drive to pull any moisture that's in that assembly or it's found its way behind the siding or roofing out of that assembly.
This is just another type of rain screen. Instead of wood strapping here, we're using a mesh product that's sometimes called cedar breather or home slicker that's behind the vertical pine siding. The black membrane you can see there is the air barrier on this house.
So here on the left is a detail of one of our vented roof assemblies in process. We have some transition taping here that's happening between our water restrictive air barrier coming down the roof and transitioning to shed water down the wood fiber insulation on the walls of our buildings. We have strapping rafter furring strips that follow the rafters up the top of the building, and then purlins that we're mounting our roofing to. Center photo here depicts the taping and air sealing around our windows, and proper detailing and flashing of our sills to shed water as they hit the window and run down the face of the building, so it sheds water over where the cladding will eventually be. There's a similar set of photos in that same sequence. How you can see how the strapping, horizontal strapping here on the left, is how we're mounting our extension jambs and siding. Similar with the plaster detailing around, connecting to the window and shedding down onto our metal sills. The photo on the right is just a depiction of how plaster can act as natural lime plaster can act as a water barrier, air barrier, and a vapor open vapor variable vapor retarder. We'll get into that in a little bit.
When designing a house, you want to be able to draw a continuous line using a pen that indicates the control layers, unbroken control layers. And in this case, this is showing an air barrier that's at the interior of the finished surfaces.
So similarly with the interior of the building, we want to be able to create a line shown in red here that goes all the way around the inside of our conditioned envelope. We also want to have that air barrier running depicted with the dotted line here around the exterior side of our envelope. So we're encapsulating our walls, roofs, and foundations on all 6 sides of the building. We can see those transitions of those junctions where our foundation meets the walls. We want to be able to tape those seams and air seal them. Similarly, we want to be able to, where we have vapor barriers underneath our foundation slabs, we want to make sure we're getting good connections at those transitions.
Just some graphics that depict air barrier on the left there, and the critical components of your entire assembly. You need to pay attention to the roof, the walls, the windows and doors, the skylights, foundation walls, the slab, and all of the intersections. And on the right there, a beautifully complex house with lots of nice high performance membranes and products. So just a little introduction to the difference between air barriers and vapor barriers. Air barriers control energy loss, and they need to be as close to 100% continuous as possible. An air barrier that's only 98% effective is not going to do a very good job and give you great results. You need it to be 100% implemented. By contrast, a vapor barrier that is 90 to 95% effective will stop the majority of the vapor. So important distinction there. But the air barrier and air-driven moisture is one of the number one concerns. So you need to have a good air barrier. A vapor barrier alone is not going to accomplish the goals of protecting the building envelope. Air barrier will stop moisture transport through air movement. And the air barrier can be created with plywood, membranes, sheetrock, some insulation types. There's a number of ways to do it, and it can be made of multiple components as well, as you'll see in some of our upcoming slides. That the air barrier can transition from one material to another, and from one location to another. A vapor barrier, air carries water in the form of vapor all around the building. This is particularly important to understand to control durability in our assemblies. So a vapor barrier will control moisture transport by diffusion. So that's moisture that's in the air and is moving into the assembly through the building materials, not with air, but just by the natural movement of water. Uh, Heat and moisture wants to move from where there are higher concentrations to where there are lower concentrations. So from where it is warmer to where it is cooler. So generally, our heating season is when we're concerned about this stuff. Um, and so we will talk in about the permeability of different materials and how they stop the movement of water, or conversely allow a certain amount of moisture to travel through them. The higher the perm rating, the more vapor can pass through the material. Here we see the perms of various building materials. The blue, the Stego-Crawl, is a plastic 15 millimeter vapor barrier intended to not allow moisture transport. So you can see that it falls into the vapor barrier class 1. Then between 0.01 and zero point 0.1 is a vapor retarder class 1. And the next level up is vapor retarder class 2. Let's see, in the vapor retarder class 1, you've got your also plastics that are thinner. So even those plastics do allow some moisture transport. Then you've got your asphalt coated craft paper, felt paper that you'll see on some older houses. And then as you move up into semi-permeable class 3, you've got latex primed and painted, that's sheetrock. And then you've got your yellow is some sort of weather barrier. And then plain sheetrock that's not painted has a higher permeability rating.
So one of the things we need to be thoughtful and are mindful of is that when we combined our air barriers and vapor barriers and these materials within our assemblies, we need to be careful about creating what they call a vapor sandwich. So we want to make sure that ideally we're using air barriers that are vapor open, that are in that vapor retarder category and have a high permeability, or that are vapor variable, or is sometimes referred to as smart vapor retarders. And what that does is it stops air from getting into that assembly, but it allows vapor to diffuse through that cavity. Which also means that seasonally, if we have that rain screen strapping on the outside of the building, or we're cooling our building on the inside, that moisture, the humidity, the vapor that gets into that cavity has the ability to dry to the outside of the assembly.
Ryan, I think we got to pick up the pace a little bit.
We're about 34 minutes in, or 35 minutes in, I think.
Okay, it looks like we got like 17 or 20 minutes before we should start taking questions.
Okay, sure. Another area that is critical is if we have flat roofs or a vapor closed roof membrane, we just need to be mindful about using spray foams in those areas, because they can cause that vapor trap that we were referring to.
If you have moisture moving through a wall, you'll see it gets to a point where it hits the dew point and where it condenses and freezes. And in this photo, the moisture has gotten through the fiberglass, frozen, created a layer of frost. And this is a condition that happens out there all too often.
One way to help keep that from happening is by using these intelligent membranes, or vapor variable vapor retarders, on the inside and outside of our buildings. Some of the ones that Ethan and I like to use are from 475, are distributed by 475. They're from a company called Proclima. And this is the Mento 1000 on the exterior. They also have an Intello membrane on the interior.
These materials, somewhat miraculously, have a low permeability rating when the relative humidity is lower. But when moisture does get into the assembly, the permeability rating changes. And so, yeah, pretty fascinating. I don't really know the physics of it. Haven't heard anybody really explain it, comprehensively. But that's what these materials do and claim to do.
Yep. There are some great videos on 475 building website that kind of delve into those physics a little bit deeper. I don't think Ethan and I are qualified to do that here tonight. This is another pictorial kind of talking about or illustrating that that diffusion happening in the wintertime. Moisture can, vapor can diffuse through the cavity, but moisture is held out. And in the summertime, any moisture that finds its way into the cavity can dry to the cold, to the colder, drier indoor conditioned environment.
Yeah, going from 0.13 perms to 13 perms. Yeah, pretty impressive.
Yep.
So yeah, just some different ways to accomplish an air barrier. You got the zip system on the left. You've got the Henry Blueskin on the right, and in that project, looks like they're installing rigid mineral wool boards over the top of the Henry Blueskin. On the left there, you've got a spray applied membrane. Tremco is one of the companies that does those kinds of applications. And then on the right there, you see some studs that have had a whole lot of caulk applied to them.
I've had New Hampshire building inspectors make us do this.
No kidding.
Yep.
Some Intello looks like utilized at the ceiling. When you're using that for an air barrier at the ceiling, you can install some strapping so your wiring can stay to the inside of that air barrier. And then you'll sometimes drill some holes in it, cut some holes in it, blow the cellulose in there that you can see poking out, and then oftentimes, most of the time, you'll tape up those holes.
Yep.
So this shows a typical double stud wall and some roof and slab details. And the thing I want to point to here is the idea of the floppy bit, which is a really effective strategy for transitioning the air barrier from the exterior plywood in this case, and that's what Ryan's pointing to here, is this black membrane which comes over the top plate, and then the roof trusses are set atop that, and then the air barrier, once it gets to the inside, runs along the bottom of those trusses. So floppy bit is actually a technical term to refer to the materials used at these transitions. This is just a few different intelligent vapor retarders that are available in the US market. Here we're showing that when you're doing an energy retrofit, there can quite often be a number of conditions and a number of different details in the assembly. And so in this case, the air barrier exists to the outside of the framing in some cases. There's vent cavities on top of the sheathing over in the detail on the left, and over on the right, it uses the same floppy bit transition that I was describing in the previous slide.
Another example of the floppy bits in play here.
In this slide, you can see that the main volume, the larger volume, the air barrier is that hydro gap material there that then transitions above those windows to the bottom of the roof trusses. Whereas on the left, because it was an existing volume, the air barrier travels up over the top of that sheathing, and then you have an air space vent cavity above that sheathing, and then a second layer of plywood.
One of the things that's important to do is also think about the sequencing is that's what the floppy bits are doing, is allowing us to install that air barrier that we can then tie into the assembly as we're putting it together. So similarly, we can see that on the second floor with the flat ceiling, we've installed the vapor barrier, strapped out the walls, and then we frame our interior walls. For cathedral buildings or cathedral ceilings, oftentimes what we'll do is set blocking between our rafters, then install strips of the interior air barrier and vapor control layer. And and then frame up our walls underneath that.
One assembly we like using on certain projects is a cross-strapped wall. In this case, 8 inches. So on the right, you can see this is a 2x6 wall, and then on the inside of it, over the next one over to the right, yeah, slide back, but yeah, there you've got 2x3s in this case that are applied horizontally to minimize thermal bridging, and you end up with an 8-inch wall that we fill with cellulose. You can see the floppy bits in the middle, and then and here's a picture of it in action during a recent team meeting. It's the only picture I had of it, but that you can see cross strapping there. So now we'll transition into talking about building air tightness and how it's measured. It's done with a blower door. This is what it looks like. It's a fan that you install in one of the doors, and on the upper right there, you can see that's the manometer reading the cubic feet per minute of air moving across the meter in that fan. And we convert the reading of cubic feet per minute into air changes per hour, ACH 50. Air changes per hour at 50 pascals. And CFM stands for cubic feet per minute. So for an example house, say it's a 2,000 square foot house with 8-foot ceilings, 2,000 square feet times 8-foot ceilings gives you a volume of 16,000 cubic feet. So if the fan in this picture is measuring 3,136 cubic feet per minute at 50 pascals times 60 minutes, it means there's 188,160 cubic feet moving through that fan each hour. So divide that total volume of air by the volume of the house, and you'll see that this house has 11.76 air changes per hour at 50 pascals, which is typical, in the range of typical for many existing homes. It's a little high, but it's typical. For reference, some standards that exist in Vermont, the Energy Code now requires less than 2 air changes per hour for any new built homes. New Hampshire, by contrast, has a standard of 5 air changes per hour at 50, which is not very good and not hard to achieve. It was briefly at 3 air changes per hour before it was rolled back. The passive house standard is 0.6 air changes per hour at 50, which takes some effort and planning to achieve, but is quite attainable.
Yeah, and for reference, I don't know if you guys remember that slide, but the slide on air tightness was indicating that the same building that had a 5 air change per hour air tightness, if all we did was make it tighter down to 0.6 ACH 50, we would reduce the building energy by 60%.
So here's an example of a house we built in Norwich a few years ago, designed by Backtilt Studio. It won the Efficiency Vermont's Best of the Best, a 4-bedroom house. It is only 1,280 square feet, and that's the total footprint. So in this case, the 1,280 square feet does not subtract for the 1-foot walls. So it's less than that in terms of living space. But the ceiling is R60, and that's a measure of the thermal resistance, and the walls are R41. This manometer reading was 156 CFM, so 12,800 cubic feet, 82 minutes to fully air change the volume of the house. That equals a 0.72 air changes per hour at 50, which is not hitting the passive house standard, but did meet Efficiency Vermont's high performance threshold of 1 air change per hour when this was built. This is my house in Lebanon. That was one of the houses in the energy use intensity slide, built in 1870. It's undergone a shallow energy retrofit. The walls had no insulation in them whatsoever. We drilled them and filled them with cellulose and then sealed those up. Initially, the blower door gave us a reading pre-work of 7,531 CFM 50, which equated to 19 air changes per hour. After work, we got it down to 1712, which equates to 4.3 air changes per hour, a 77% reduction. And the reason it hasn't gone further than that is because the house still has most of its old windows and its old doors, and those are the sources of air leakage.
Here's a project that we worked on at the Meriden Library with the town of Plainfield. It's a pretty simple geometry. There are two intersecting volumes, total of 3,600 square feet. We were able to achieve 0.27 ACH 50 in this building, which is well within passive house standards. We actually I reached out to one of the building managers with the town there today and was able to find out their kilowatt hours per year consumed divided by the square footage for a total EUI of 3.8 kilowatts per square foot, which is pretty cool.
That's great. So it is important to seal your windows. And the best way to do it is with good high performance vapor open tapes. You don't have to use vapor open tapes, but that's what this is depicting here. Some of the Tescon Vanna products that we use quite often. And another diagram showing it. Ryan, will you jump to the weatherization slide? We got a few more minutes.
Sure.
It's just the next one here before we do our, yeah, okay. So just if you want to weatherize a home in New Hampshire, it's worth applying for New Hampshire Safes. You go to newhampshiresaves.com and only qualifying homes are eligible for up to $6,000 in rebates and in matching incentives. In Vermont, anybody can get incentive money for making thermal and energy efficient improvements to their home. And you just have to call an energy auditor who is part of Efficiency Vermont's Efficiency Excellence Network. Happy to talk to anybody more about this, but in response to one of the questions in the chat, if you want to tighten up your home, the energy audit is the place to start.
Yeah.
On the next slide, I'm showing you what it looks like at the newhampshiresaves.com site, where you can enter your energy use information and it will let you know if you qualify for the program. If you do, you get a free energy audit and then the incentive money to perform the work. Just these pictures show some things that we see all the time. The top left is a house that's clearly showing heat loss through the roof. And can indicate that there's some opportunity for improvement. And yeah, want to just okay, so you want to put in okay.
Sorry,
So we've got some slides here. We're just about out of time,
yeah.
but what we did want to mention is that recently there's been some really exciting work done by some colleagues of ours at New Frameworks and Builders for Climate Action. And what they've done is a huge amount of work to analyze and make visible to us the carbon emissions of building materials. And they are measuring it right from the production stage and the extraction of the resource all the way through to the end of life. And that's what this slide shows. And it's a really exciting new frontier in high performance building. And in a nutshell, what it's telling us is if we build with naturally based materials, and the best of which is our agricultural byproducts like straw, which are 100% effective and time tested, we can do a good deal to make our buildings actually carbon sinks. And happy to talk more about that. But we are just about at the end of our time. And if we have time post questions or during the questions, we can get into some of that a little more. Maybe we should go back to the summary slide, Ryan.
Yeah. Yeah, so key takeaways. Our first lever of impact is the building size and geometry. And then we have air tightness, make it tight, ventilate it right. We can talk a little bit about that ventilation if you guys have further questions. And then, yeah, just designing for durability, getting the details right for how we're transitioning between the shedding of the water, the flashing of the windows, using the right interior and exterior air barriers and vapor retarders, and when at all possible, utilizing bio-based regenerative materials that Ethan was mentioning there at the very end. I think we can open it up to questions here. I can stop my share and
Yeah, well, thank you so much, Ryan and Ethan. You have managed to pack in a lot and explain it really well, and I'm tremendous amount of great information. So just again for questions, for questions, if people are okay with using the raise hand feature, just go to the bottom of your screen to where there's a little heart and it says react. And if you click on the up arrow, wow, it's different for me now. It's not showing the raise hand.
see one from yeah, Nancy Whiteman,
Oh,
maybe.
there it is. Yeah. Okay.
For an
Sorry.
old house with
Go ahead.
cellulose, yep. For an old house with cellulose, is it reasonable to retrofit a second external wall to mimic your double stud new building project?
It is reasonable. It depends upon all of the other variables and conditions of the house. If you were going to do that, an exterior cavity that's exterior of the existing home or of the structural portion of the home is sometimes referred to as a Larson truss. So yeah, this is something that people have been doing for a long time. And say, for example, your house needs all new siding and windows anyway, and you want to add some insulation, that is a perfectly reasonable place to consider adding it. There are obviously other considerations in the planning process, but yeah, it's a very effective solution.
Yeah, it could also be a great candidate for an exterior rigid insulation board, like the wood fiber insulation board that we were discussing from Timber HP or from Gutex or Styka. I think, okay, Walker Stevenson has.
Why? Thank you so much. I just wondered if you build a really airtight house, how do you ventilate it?
Yeah, so the ERV or HRVs, we're primarily using ERVs in this climate, and what that's doing is it's bringing in, and the code actually specifies this, you know, a certain CFM per occupant in the building, depending on the use group of the building. The total number of CFMs per occupant changes, but for houses, I want to say it's 10 or 20 CFM per person. I don't know off the top of my head, but the idea is that we're sizing these ERVs, and then based on how many occupants are in the building, and then the energy recovery ventilator is what it's called, is taking fresh air from the outside and distributing that to the indoor living spaces, and then we're extracting stale, moist air from our bathrooms, kitchen, and pulling that to the outside. The energy recovery aspect of the ventilation, the ER of this, is actually what we're doing is mixing that air. Actually, excuse me, we're running that air through a ceramic core that has like almost like cardboard like tubes in it that is allowing that air to pass and warm up or kind of precondition that core as that conditioned air is exiting the building. It's preconditioning the exterior air coming in. So that's how it's recovering some of that energy and not just dumping unconditioned air in your home. The other couple of aspects of ventilation that are also important to think about is when we're building houses more tightly and more efficiently. Traditionally, we've been using fossil fuels to cook in our homes, and one of the things that we need to be really careful about and actually heat our homes as well is Our fire, code today says that our fireplaces that we have in our homes need to be like closed combustion stoves, so a door that actually closes and seals. We need to bring in fresh air mechanical ventilation for that stove, the wood stove. Similarly, with our ranges in our kitchen, when we have a gas range, when at all possible, we actually like to use, electric induction ranges or electric ranges as opposed to a fossil fuel burning cook stove. But similarly, we need to have an exhaust to properly exhaust propane or the gas that's building up in the house as a result of that combustion. And one of the key things that I see often in this industry at this point is that the builders are making the buildings tight, but they're not actually getting the proper mechanical ventilation to those cook stoves, and which is super vital, because what ends up happening is if we're only exhausting air out of the building, we're not bringing in balanced ventilation to that cook stove. What ends up happening is you put the building under a negative pressure pretty quickly, and the efficacy of that hood or exhaust is now failed. It's like pinching the end of a straw. You can only, suck for so long. And so, those gases can build up in the home and cause a really unhealthy indoor environment. So having the ventilation properly sized is really critical. And in many cases, I've had clients who are just super insistent, like on having a gas range in their house. And so we'll work with an engineer to do so. And I've seen it, almost double the cost. You have a nice gas range in there, a nice hood, and essentially what you pay for both of those components, you're going to pay for again in getting the ventilation for them right.
Yeah. So yeah, Walker, there are code-defined standards for bringing fresh air into buildings, and so design of a balanced ventilation system, as Ryan explained, is a critical piece of a new home. And when you have an existing home that needs fresh air, sometimes you have to get creative and can't deliver it as uh, to all of the spaces the way you can with a new construction, but that's okay. More fresh air is better. There's a couple of different kinds of ventilation systems. Most of them are ducted, some are ductless, and you can also have exhaust-only systems. There's a number of ways to go, but a fully designed, balanced energy recovery ventilation system is optimal.
Thank you.
Richard Thompson.
Yeah, so I'm not familiar with this wood fiber insulation that you mentioned, and so I have got a lot of questions, but probably primarily first how it compares to rock wool, but also even just in general, how long has it been around?
I believe it's been in use in Europe for some decades. And so it's a good product. One of the comparison points for with mineral wool is, well, there are a couple of them. Mineral wool takes a lot of energy to make. Mineral wool is made of rock that is heated up and spun into a fiber that can perform as insulation. Whereas wood fiber is generally sawdust or scrap logs turned into a product that puts that wood and that carbon into the building for the life of the building. So much better from a carbon standpoint. Also, the wood fiber products are coated with and impregnated with a wax product that makes them shed water, whereas mineral wool tends to absorb water and it's drainable. Yeah, I'd say the wood fiber is superior on a couple of levels, but mineral wool has its applications for sure.
Yeah, I think to that point, Ethan, the mineral wool would be, a good option, maybe in carbon, if we're worried about that embodied carbon, maybe in carbon reduction, when used around a foundation compared to EPS foam, allows for drainability. But utilizing that the right material and the right part of the building is pretty critical there. The wood fiber, the other components we didn't really get to talk about today, but actual ease of install. So one of the things that we experimented with using the wood fiber, or excuse me, the mineral wool on the exterior of our buildings, but our carpenters didn't like using it because they had to spend a lot of time as we were running our strapping, through that mineral wool, it would compress a lot. And so keeping the walls nice and straight, keeping our window trim nice and aligned was a chore. And so the nice thing about the wood fiber board is it's very dense. Depending on how thick it is, when it's on the roof, you can actually walk on it. It's not technically a structural sheathing, but in some cases, it's a very rigid product comparatively. And to Ethan's point, it does, significantly, in this case, it actually sequesters carbon in the material itself versus, the mineral wool and polyisos, EPS foams are all going to be, essentially contributing to a bunch of carbon equivalent or carbon into the atmosphere in their production and manufacturing.
I think I want to jump over to some questions that came up in the chat and touch on those, make sure we don't miss them. So Ben says he wants to make his house more efficient for all the reasons, so an energy audit is a really good place to start. Same thing to Richard, who lives in a plank house, and we have Dodd has had his house weatherized, and he also lives in a plank house. An energy audit is a really good place to start, and as we've indicated, air sealing, taking a look in your attic and crawl spaces, knee walls, seeing what opportunities exist to tighten up the place. That's a good step one. And then we had somebody saying they decided to not do mechanical ventilation as it's vulnerable to electric service disruptions. Fair point, but in an extended power outage, you can always crack the window if you need some fresh air. But happy to talk about that some more. Mark asks if there's a commercially available method to optimize how forced hot air ducts are laid out and controlled from furnace to all living area. And yeah, there are all kinds of formulas and methods for designing effective duct distribution of heated air or fresh air, whatever it is you're trying to deliver. And unfortunately, to get a system that is fully optimized and requires an engineer and can cost a little bit of money, but it's not hard to get one that gets you where you need to go. So yes, there's lots of methods to get effective duct distribution for whatever air it is you're trying to deliver.
Yep. We got Julie Colt.
Hi, everyone. Thank you for your presentation, gentlemen. Do heat pumps offer any benefit in terms of bringing fresh air in?
No. So heat pumps are not going to be bringing in fresh air into the building. They're working by having a compressor outside that's heating or cooling a refrigerant that's run in a line set or a grouping of copper lines and control wiring that runs to an interior head supply head that's mounted on the wall behind you. Actually, it looks like, and so that supply head is then taking that refrigerant and blowing air past the refrigerant lines and heating the air that's in the space. In some cases, they can naturally help, minimally help dehumidify the space, but it's not significant.
Okay, great. Thank you.
Let's see. Do we have any other
There are a couple
questions?
questions in the chat. Are ERVs possible to install in a cathedral ceiling home as a retrofit?
Yeah. So there's Ethan was mentioning that there's a number of different types of ERVs. or HVAC, ventilation products on the market. One of these, depending on the type of home, if you don't have a basement, you could you can look at putting the units in a mechanical space or a basement. If you don't have that available either, you could look at a product. I believe it's called Lunos. They make a product called E2. These are wall cassettes essentially that are products that like actually get cut into the wall. They do require some power, so there may be some. They do require power to work. And essentially, what you do is you put these units on opposing walls in differentiating or different rooms in the house. And for like 30 minutes out of the hour, they'll, one fan will pull air in from the outside, the other will push air from inside to the outside, and then they alternate. So essentially, they're working with the same principles, but they can be kind of remotely set up and don't require ducting, right?
There's another question in the chat. Is it necessary to use triple pane windows to achieve passive house standards?
This is a good question. So I think potentially yes, if you reduce the number of windows in the home. And so it's a great question. I'm not
I
actually.
mean, yeah, there are some remarkably good double pane windows out there right now. And I guess I think it's also worth pointing out that the passive house standard, while a very high standard, uh, is, doesn't take all of the factors of energy consumption into consideration. Um,
Absolutely.
so, for example, it is easier to achieve a passive house standard with a larger house, because a larger house can use less energy per foot. The energy use intensity number can be lower. So, and whereas a smaller house can use a lot less energy. Now, if you're going just for the passive house standard, it depends on how much solar gain the house has, what other sorts of appliances are in use in the house, how many people live there. All of that goes into the passive house model and are considered passive gains. And if you model it, you might find that with very good double pane windows and not very many windows, as Ryan is indicating, you might be able to hit the passive house standard without triple pane windows. So it's a good question. Also worth noting that the passive house standard for energy use intensity is different in Europe than it is in the US. And there's a longer story there, but it varies by region in the US. How much energy you can use to qualify for passive house varies by region in the US.
Looks like Julie has another question.
Hi there. So I have a heat pump, which you can see behind me, which I love, but I also have a propane fired high efficiency furnace with ducts into rooms. Is it possible in a retro to use that ducting system for bringing fresh air in?
Yes.
Circulating, can something be done to circulate fresh air in the home?
Yeah, absolutely. I actually have that an integrated ERV into the forced air system that we have in our house. It's one great way of kind of continuing to condition that air. I think it's definitely depending on when the house is built, it's worth getting making sure the ductwork is in good condition, that it's cleaned, and that that if there's any, depending on how the duct is running, like nowadays, we need to make sure that if that ductwork is running through uninsulated areas of the assembly, that the ductwork itself is insulated. So I don't know if is the ductwork, yeah, we can get into a very deep dive here, but is the ductwork itself in use, like you're using that distribution in the house currently, or no?
I am on really cold mornings. I'll fire up the propane heater, get it up to 64 and turn it off,
Yep.
and use the heat pump.
Yeah. Cool. Yeah, I mean,
Yeah.
go ahead.
Oh, yeah. So, Julie, the answer is yeah, but just to reiterate what Ryan said, and there's different schools of thought on this. You can distribute fresh air with an existing ducted system. You sometimes can find that it's not the best way to go. Some people will discourage you from it, and others will say it's possible. For example, it will deliver the fresh air more effectively when your heating system is running. If you just want fresh air when your heating system is not running, your ducts might be too large to deliver that fresh air at the speed that you'd like to have it delivered. But it can be done.
Okay, great. Thank you.
Yep. There's also a lot of advocates these days for continuous ventilation. I know that for a long time, that building code was kind of allowing us to get away with only ventilating our bathrooms with humidistats. One of the kind of the big movements nowadays is continuous, getting the ventilation sized properly, the amount of CFMs are being introduced into the house sized properly, and then having that continuous ventilation.
There's another question in the chat. Our house was built in 1998, at the time reasonably energy efficient. I have the feeling that windows have improved since then. Is replacing cost efficient? I worry a little about the styrofoam constructed roof panels. Are those still used? I believe it was Winter who made those panels, lifted in place by crane.
Nice. Yeah, I think an energy audit, to Ethan's points earlier, would be a great place to start with an existing home. Windows have certainly come a long way, but that's not to say, that if an older casement window has like a good seal on it, that can be potentially, the seal can be replaced if they're no good anymore. But the windows indoors are, playing somewhat of a factor, but generally speaking, if it sounds like maybe a SIPS panel house, it's probably pretty energy efficient, and you may need to look at just where you can tighten up some of that air sealing. And the energy audit would certainly tell you, especially this time of year, when we have a nice warm indoor environment, to be able to use thermal imaging cameras while that blower door test is going on, to be able to really identify all of those areas where that leakage is occurring, would be a super great place to start.
Yeah, windows, right, are generally considered not the low-hanging fruit when it comes to energy efficiency improvements. You want to start with the interstitial spaces and the remote spaces like the attics, knee walls, and air sealing is a good place to focus your energy and money. But after that, yeah, you can start thinking about the windows, and you can do some cost benefit analyses to see what the payback period would be. But oftentimes, just having some more functional windows can lead to more comfort, and save some energy as well. So, um, certainly worth discussing and exploring. Nancy asks, is there someone, a site evaluator or architect in the area that can create a long-term plan for incrementally retrofitting a very old home to become airtight in a sensible and economical sequence? And I appreciate Dodd's answer. He points out that that's the kind of thing that we do at Earthshare Construction, and we do it for a number of reasons. And my to get on my soapbox for a second, I believe that the practitioners of our trade, the architects, the builders, all benefit from ongoing education and these kinds of conversations, because the way to do it is not straightforward. And it, because it involves balancing a lot of conditions, budget, long-term planning for a house, but it's a really smart way to go. It's just not a way that we are traditionally accustomed to going. So starting with an energy audit and then, finding an architect who is willing to work in that way and design other renovations that can be implemented sequentially. It's so the answer is that finding a team of collaborators who know how to incorporate these elements in planning is what you need to do, and that involves education on for all parties all along the way, which is kind of exciting, but also can be tricky.
Yep. Jonathan Chaffee asks, can you go back over the perils of vapor sandwiches in common wall insulation and the placement of intelligent membranes to counter that? So let me see if I can share this real quick. Okay, I think you guys can see my screen here at this point.
Yes.
In this particular scenario, we have exterior foam sheathing that's taped with tape seams. So that it's foil face foam. The foil on this and the tape are acting as our water restrictive, or this particular builder's. It's not one I would advocate for personally, but it is acting as a water restrictive membrane as well as the air barrier on the outside. It's also a vapor retarder on the outside of the building. There's a actually not craft face, it's just unfaced fiberglass batt insulation with polyethylene taped up. This is a detail that was very popular in the building industry for our own ignorance, even as late as 2010, 2015. And so the issue with this is that the polyethylene is also has a very low perm rating, and so any leak or issue with flashing around the windows or penetration in this membrane, presumably on the inside of this polyethylene is going to be sheetrock, and so if that sheetrocker installer is blasting screws because they're missing studs through that assembly, you then have penetrations in that vapor assembly, or the vapor retarder in this case, and not a whole lot of opportunity to dry. I think one of the things that the reason why we strap the exterior siding with a vapor open, like vapor variable or smart vapor retarder, and strap the inside of our buildings as well. So I'm trying to get to one of these details in the slides. Is that we create channels where we're actually, part of this strapping is actually controlling the penetrations that we're making. That strapping is getting anchored to the stud and making a nice strong connection penetration with that stud, sealing that air barrier on the inside of it. And then the sheetrock itself, we're often using just 1.25 sheetrock screws with 1-inch strapping on the inside, and so the sheetrock screws aren't penetrating that strapping. And so we're limiting the amount of air and vapor and moisture that can get into that cavity. And we're also allowing opportunity for any of that vapor and moisture that gets into the cavity to come out because of the type of membrane that it is. Hopefully that made sense.
Yeah, the intelligent vapor retarder will go generally at the inside. And some of the membranes we use at the exterior, they do have they have permeability that allows for drying as well. Some of them also have that variable vapor permeability. But yeah, this is where we install them, at the inside of the house, beneath the finishes.
Yep. And then, similarly to the outside of the house as well, we have vapor open, vapor variable membranes on the outside of our houses as well for the same reasons. So let's see, there's another question.
We have we're coming very close to 8:30, but if you are willing to answer, there are a couple more questions in the
Yeah,
chat.
absolutely. Yeah, the other thing I was going to put up here real quick is sorry, I'm trying to navigate too many screens here at once. Apologize. I do have Ethan and I's contact here that I'll pop up on the screen. So you guys, if you want to take our information down, you can reach out to us.
Great. So Nancy asks, given innovation, how frequently should one do an audit? A really good question. I mean, you shouldn't have to do it very often, but sometimes an audit is done and weatherization measures are implemented, and there may still be additional opportunities to save energy. So I would say it's never too soon to ask those questions and have those conversations. And only through having those conversations can one possibly determine if there are further opportunities for improving efficiency. But we've certainly done energy audits in houses that have been weatherized and found additional opportunities. So, yeah, it's worth doing. And Beth asks, in a tight home where basement walls are insulated with 2-inch polyiso, what options are there to insulate basement ceiling to reduce cold floors in the first floor without causing moisture issues? So the basement is insulated at the walls and the floors above are cold. I would say have an energy audit and figure out why it's cold in the basement and where can you either stop air from getting into the basement or add some additional insulation in the basement so that it's less cold down there. And there may be other solutions to that issue as well. I guess it would be house specific. We need to know more about your house.
Yep. Understanding if that slab is insulated, if there's a vapor barrier underneath the slab, are also important factors for controlling moisture in that space as well.
So Cynthia says she's heard that in a lot of cases, moisture building up inside creates more mold and material failure issues than does moisture coming from the outside. Is that your experience? I would say no. My experience is that most wall failures and rot repair jobs have to do with buildings that aren't flashed right and water coming from the outside, getting behind a deck or behind a window, behind the siding, or sometimes from the ground, if the groundwater is not running away. But it is also true that moisture coming from the inside can create severe problems.
Yeah, I think we touched on it a little bit in the talk. Specifically with cold climates, we're heating our buildings for most of the months throughout the year, and so we're creating a warm, moist, high pressure environment inside, and conversely, there's a cold, dry, low pressure environment outside, and so naturally that moisture is heat is going to those molecules are expanding and wanting to get to the outside of the building, and so they're going to find every little nook and cranny, and so that's where we do need to be mindful of moisture. A lot of times in the drier months, if we've been living in a less efficient home, it's probably really common to have humidifiers going all over the house. One of the things we talk about when we're building new homes for our clients is that they need to be mindful of indoor humidity, but also to get a humidistat so that they can actually control how much humidity they're putting into the home, because they can cause issues when we're building. They can over humidify the space, based on how much ventilation's happening or has been designed for the space for the occupants. To Ethan's point, a lot of times that moisture is primarily coming in from the outside. It certainly is if any of you have family or second homes, down south in southern climates, they have almost the opposite. In South Florida has almost the opposite physical phenomenon happening, where you have a really high pressure, hot, humid environment outside, and we're cooling our interior environment, and so you have this huge vapor drive that's moving in the opposite direction, and can cause a lot of problems beyond just hurricanes and wind-blown rains and stuff like that.
Antoinette asks if she needs a consultant on vapor and humidity reaching the underside of the final roof membrane. Who can I find? Antoinette, feel free to reach out to me, and if we can't help, we'll work to refer you to somebody. It's the kind of problem that we enjoy helping people solve. Sometimes it fits into the work scope of an energy audit, and there are other folks who do more deeper building forensic type investigations, but it's certainly the kind of stuff we do.
Ryan, were you gonna post your contact info right now? We're looking at your
Sorry.
desktop.
Oh, I'm sorry. Shared the wrong screen.
Thank you, Joanna.
But I can also, are you willing to let me send people a PDF of your slides?
Yeah.
Yeah, we can do that as well. Julie asks, she says she's interested in ADU and she has an oversized double bay garage, which with insulation and sheetrock. Is it economically better to use this existing space or create a new ADU? I mean, I guess one would have to take a look at it and see the condition of it. But if it's space that's not being used and it has a roof and a foundation and it's can be converted, then it arguably could be much economically better to utilize the existing structure, but it depends upon the specifics of the structure.
What is ADU?
An accessory dwelling unit.
Ah, okay.
Yes. Yeah, which is a great way to create more housing, and more towns and municipalities are making it easier to create ADUs.
Yep. Have you guys seen the contact or emails for contact here?
Yes.
Okay.
Yes,
Apologies.
and I can also provide that when I send out the recording
Yep.
link. So Ethan and Ryan, you guys are amazing. This is incredible information. So thank you very, very much for everything you've shared with us today.
Yeah, I really appreciate the opportunity.
Joanna, thanks so much for doing this, and thank you everybody for coming. Thanks for your questions, and hope to talk with more of you soon.
Ethan, you want to talk about the BS and Beer group a little bit?
Yes. Oh, sure. Okay. Yeah, I see what you're saying. I gotcha. Yeah, so we have a group that meets monthly at Salt Hill in Lebanon. BS and Beer is Building Science and Beer, and it's a group that was started in Maine, and now there are chapters all over the country. We meet the third Thursday of the month. If you Google BS and Beer Upper Valley, you'll find the back page of our website where you can sign up to be on the email list. This month, it's actually happening on the second Thursday, next Thursday, and Ryan and I are giving an altered version of this talk, which because that audience is more builder and architect, building professional centric. But it's a great group, and we have a lot of homeowners and just interested people of all walks who come to it. So everybody would be encouraged and invited to come. There's also an Instagram page, but we have all kinds of interesting presenters every month of the year.
Yeah, I really enjoy the BS and Beer talks. They're a terrific resource, and a lot of interesting information and ideas come out of them.
I do have just a couple more little plugs here to make. So there was some mention over passive house design, trying to meet passive house design standards. The same group or some of the folks, Emily Montram, who was a big part of hosting and starting the BS and Beer, was one of the co-authors with Mike Maines and Christopher Briley with a great book called Pretty Good House. Essentially, a group of builders in Maine started talking about what it means to create a passive house, and decided that maybe we don't have to go all the way passive house. We can just go pretty good. And the book is a great kind of introduction into some really great construction practices. The other book that I highly recommend for folks, I don't know if this is mirrored or backwards for you, but it's Building Science Essentials book from Jacob Deveriscusen, who provided a bunch of the information. He's also one of the owners of New Frameworks Design Build and a major contributor to Builders for Climate Action, as well as the author of that book. And that's a great resource if you're interested in, nerding out on building science.
Thank you. Maybe, Ryan, would you be willing to give me the titles and authors of those by email, and I can include them when I send out the link to the recording?
Absolutely.
And can one of, is it okay if are you willing to let me share your slides with people?
Yeah, I think
Or if there's an issue, it's okay.
I would be like, I'm not personally opposed to it. I think part of, we had some very generous colleagues who gave us kind of license to use this information for the purpose of giving the talk. And so,
Okay.
in terms of, we just want to make sure, I think I would want to talk with them, and
That's fine.
I think
Totally
at the end of
fine.
the day, they want to be acknowledged, and we've tried to do in this presentation, provide their contact information, as well, so that people can. I think if you were to share the video maybe with people, it'd be a little bit easier to
Okay.
navigate that.
Got it. Got it. Okay. Well, thank you again so very much. I really, really appreciate it.
Yeah, thank you.
Thanks, everybody.
All right. Good night.
Bye.